Construction projects rank among the most complex human endeavors, demanding a combination of science, engineering, project management, financial planning, and precise human coordination. Unlike other professional fields where errors can be minor or reversible, mistakes in construction can have serious consequences, ranging from financial losses and delays to structural failures, legal liabilities, and, in extreme cases, loss of life. The stakes are high because every construction project involves numerous trades, thousands of materials, and hundreds of people working together under tight deadlines, stringent safety regulations, and strict quality control requirements. Even with the advent of modern construction technologies such as building information modeling, BIM, structural simulation software, automated project management platforms, and advanced material testing techniques, construction projects continue to face unexpected challenges and failures. Studies from global construction industries indicate that a significant percentage of projects exceed their budgets, experience delays, or fail to meet quality standards. Despite careful planning, failures often result from a combination of technical, human, environmental, and managerial factors that create a cumulative effect, rather than a single point of failure. Why understanding failure is crucial. Understanding why projects fail is not just an academic exercise, it is a professional necessity. Construction failure is rarely the result of a single mistake. It is usually the outcome of a chain reaction of errors, mismanagement, miscommunication, and environmental challenges. Recognizing the root causes allows professionals to implement preventive measures, mitigate risks, and ensure the safety, durability, and efficiency of the project. Failure in construction impacts every stakeholder. For clients, it can mean escalating costs, delayed occupancy, or financial loss. For engineers and architects, failure can result in reputational damage, legal liability, or loss of professional credibility. For contractors and workers, it may involve safety risks, penalties, and operational setbacks. In essence, understanding failure allows professionals to anticipate challenges before they occur, design preventive strategies, and manage risk effectively throughout the project lifecycle. The main causes of construction project failure. To provide a structured understanding, it is useful to categorize the primary causes of construction failure into several key areas. 1. Soil and foundation issues. No matter how impressive a building appears above ground, if the soil beneath it is unstable or the foundation is improperly designed, the structure is at serious risk. Problems such as soil settlement, heave, erosion, or contamination can cause walls, slabs, and columns to crack, tilt, or fail entirely. Professional geotechnical investigation and foundation design are critical to preventing these failures. 2. Structural design flaws. Even with a stable foundation, structural errors in design can lead to catastrophic failure. These include underdesigned beams or columns, incorrect load calculations, and failure to integrate structural, architectural, and MEP designs. Such flaws compromise the safety and durability of the structure. 3. Material defects and poor workmanship. The strength and performance of concrete, steel, and other materials are non-negotiable. Issues such as low-quality concrete, incorrect mix ratios, substandard steel reinforcement, improper curing, or poor workmanship can compromise the integrity of the building. Even minor defects, if left uncorrected, can lead to long-term structural problems. 4. Waterproofing and moisture problems. Water infiltration is one of the most common sources of structural deterioration. Poor waterproofing, inadequate drainage, or incorrect installation of membranes can lead to foundation weakening, corrosion of reinforcement, mold growth, and damage to finishes. 5. Safety hazards and labor management issues. Unsafe working conditions, lack of personal protective equipment, or poorly managed labor teams can lead to accidents, injuries, or fatalities. Beyond human risk, safety failures often cause delays, regulatory fines, or insurance complications. 6. Equipment and machinery inefficiencies. Heavy machinery and construction equipment require proper maintenance, skilled operators, and scheduling. Equipment failures or poor operational management can halt construction, compromise quality, or create unsafe conditions. 7. Design changes and client modifications. Frequent or late-stage design changes, often requested by clients or due to evolving project requirements, can disrupt schedules, create conflicts between trades, and increase costs. Professionals must evaluate the structural, financial, and scheduling impact of these changes. 8. Scheduling and cost overruns. Projects often fail because of unrealistic deadlines, poor planning, or unforeseen delays. Mismanaged schedules can cascade into missed milestones, idle labor, delayed material delivery, and eventually cost overruns. 9. Regulatory and environmental compliance issues. Failure to comply with local building codes, permits, or environmental regulations can halt construction, trigger fines, or require costly redesigns. Proactive compliance management is essential for smooth project execution. 10. Inspection and handover failures. Even completed structures may face problems if inspections are incomplete, defects are missed, or documentation is inadequate. Proper handover, commissioning, and final quality checks are essential to ensure the structure is safe, durable, and ready for occupancy. The domino effect of construction failures. Construction failure is rarely a single event phenomenon. More often, it is a domino effect, where one error triggers another. For instance, poor soil assessment might lead to an inappropriate foundation choice, causing uneven settlement. Uneven settlement stresses structural beams and slabs, leading to cracks, deflection, or misalignment. Stress-related defects may require rework, delaying schedules and increasing costs. Delays may prompt rushed labor or improper material use, compounding risks further. This chain reaction highlights why risk assessment, monitoring, and early intervention are vital to project success. Professionals must anticipate failures before they occur, rather than responding reactively. The role of professionals in preventing failures. Preventing construction failures requires professional diligence at every stage. Engineers and architects perform structural calculations, design verification, and risk assessment, ensure compliance with codes and standards, coordinate multiple disciplines. Project managers oversee schedules, resource allocation, and budget control. Manage labor and equipment, ensure adherence to safety protocols. Quality inspectors monitor material quality, workmanship, curing, and structural integrity. Safety officers implement and enforce safety standards, conduct risk assessments, and provide training. Professionals must work together as a cohesive team, constantly communicating and monitoring progress, rather than operating in isolated silos. The success of a project depends on this holistic approach to risk management, quality assurance, and proactive problem solving. Importance of learning from real-world examples. To truly understand how failures occur and how professionals prevent them, it is crucial to examine real-world scenarios. A commercial podium project near a river encountered high clay content. Engineers redesigned the foundation using a rough slab with deep reinforcement, monitored soil settlement, and successfully prevented cracks. In a multi-story residential building, improper reinforcement placement was detected during an inspection. Corrective measures were implemented before concrete pouring, avoiding potential slab failure. A high-rise project experienced client-driven changes to electrical layout late in construction. Engineers recalculated loads, coordinated trades, and safely implemented the change without compromising structural integrity or schedule. These examples illustrate that risk is present from the very beginning of a project through final handover, and professional foresight, planning, and quality control are essential to prevent failures. The goal of this video. The purpose of this video is to provide a comprehensive guide to understanding construction project failures and professional strategies to prevent them. By the end of this video, viewers will be able to identify common failure points in construction projects, understand the technical and managerial strategies professionals use to prevent failures, apply actionable insights in real-world projects, recognize the importance of proactive risk management to reduce delays, cost overruns, and structural defects. Construction is not just about erecting buildings. It is about managing complexity, mitigating risk, and ensuring safety, durability, and functionality. A well-executed project reflects engineering precision, professional diligence, careful planning, and strict adherence to industry best practices. Section 1. Soil and foundation defects. Foundations are the invisible backbone of every construction project. While walls, beams, and facades attract attention, the true strength and safety of any building originate from what lies below, the soil and the foundation. Even a structurally magnificent building can be rendered unsafe if the ground it stands on is unstable or the foundation is improperly designed or executed. This is why soil and foundation defects are among the most critical causes of construction failure worldwide. Understanding the complexity of soil. Soil is a dynamic, natural material with a highly variable composition. Its properties can differ from one location to another, and even small changes in moisture or load can affect its behavior. For construction professionals, understanding soil behavior is essential. Key factors include 1. Soil type and composition. O. Clay. Expands when wet, contracts when dry. Can cause foundation heave or cracks. O. Silt, fine-grained and prone to settlement under load. Often problematic in reclaimed land. O. Sand, good drainage but low cohesion, susceptible to liquefaction during earthquakes. O. Gravel, excellent load-bearing capacity if properly compacted. O. Rock, strongest base but requires specialized excavation and anchoring techniques. 2. Moisture content. Water affects soil strength and behavior. Saturated soils lose load-bearing capacity, leading to settlement, slope failure, or liquefaction during seismic events. 3. Load-bearing capacity. Every soil type can support only a limited weight. Overloading weak soils can lead to uneven settlement, cracking, or total structural failure. 4. Contamination and organic matter. Soils with high organic content or chemical contamination may degrade over time, weaken foundations, or accelerate corrosion of reinforcement. 5. Environmental factors. Seasonal rainfall, flooding, groundwater level fluctuation, and nearby construction activities can all impact soil stability. Geotechnical investigation, the first step in prevention. Professional construction projects never begin without a comprehensive geotechnical survey. These investigations ensure that engineers understand soil properties and design foundations that can safely carry the load of the building. Typical geotechnical investigation includes borehole drilling and soil sampling, determines soil layering, depth, and characteristics. Laboratory testing, moisture content, compressibility, shear strength, and density tests to quantify load-bearing potential. Groundwater assessment, identifying water table levels and seasonal variations. Soil stabilization analysis, determines if the soil requires reinforcement or treatment before foundation work. Without this critical step, construction is essentially guesswork, leaving the project vulnerable to settlement, cracks, or structural failure. Types of foundations and their role. The foundation type depends on soil conditions, building load, and structural design requirements. Choosing the wrong foundation is one of the most common causes of failure. 1. Shallow foundations. Used when soil near the surface is strong and stable. Types include spread footings, pad foundations, mat or rough slabs. 2. Deep foundations. Required when the upper soil layer is weak, compressible, or inconsistent. Types include piles, driven or bored, caissons, drill shafts. Each foundation type has specific engineering requirements. For instance, rough foundations distribute loads evenly, while piles transfer loads to deeper, more stable strata. Common soil and foundation defects. 1. Differential settlement. Unequal compression of soil causes slabs, walls, and columns to crack. This is often subtle initially but grows over time, leading to serious structural issues. 2. Heaving. Expansive soils push foundations upward, causing floors to warp and walls to crack. 3. Erosion. Rainwater, surface runoff, or poor drainage can wash away supporting soil. 4. Liquefaction. Saturated, loose soils can temporarily behave like a liquid during seismic events, destabilizing foundations. 5. Contamination and corrosion. Soil with chemicals, salts, or organic matter can corrode steel reinforcement and weaken concrete over time. 6. Poor drainage and water accumulation. Standing water around foundations reduces soil strength, increases settlement, and accelerates material deterioration. Professional strategies for prevention. To prevent soil and foundation failures, professionals adopt multiple strategies. 1. Early soil testing and analysis. Conducting a thorough geotechnical study before design begins. 2. Soil stabilization techniques. O-compaction. O-chemical treatment, lime, cement stabilization. O-use of geogrids or soil replacement. 3. Appropriate foundation design. Matching foundation type to soil conditions, load requirements, and environmental factors. 4. Drainage and water management. Installing proper perimeter drains, French drains, and slope grading to prevent water accumulation. 5. Settlement monitoring. Using inclinometers, settlement markers, and laser leveling during and after construction to detect movement. 6. Periodic inspection and maintenance. Continuous oversight ensures that even minor shifts are addressed before becoming major issues. Real-world examples and case studies. Podium slab near river with clay soil. Engineers identify expensive clay. They installed a reinforced rough foundation, monitored soil settlement, and prevented cracks. High-rise on reclaimed land. Variable soil required deep piles and soil compaction. Continuous monitoring ensured long-term stability. Industrial warehouse on mixed soil. Early cracks due to differential settlement were corrected by adding additional piles and improving drainage, preventing structural damage. Residential building on hillside. Soil erosion and slope failure risk was mitigated by retaining walls, soil anchors, and proper drainage. Lessons learned. 1. Foundations are the first line of defense in structural safety. 2. Early investigation saves time and money, catch soil issues before construction begins. 3. Continuous monitoring ensures long-term performance. 4. A holistic approach, considering soil, drainage, environmental factors, and foundation design together, is critical. 5. Real-world examples show that professional diligence, monitoring, and proactive measures prevent failure, even in high-risk soils. Section 2. Structural design flaws. The strength, durability, and safety of any construction project depend heavily on structural design. A well-designed structure ensures that every load, from the weight of the building itself to environmental forces like wind, rain, and seismic activity, is properly distributed and resisted. However, structural design flaws are among the most common causes of construction failure, often leading to cracks, deflection, excessive vibration, or even catastrophic collapse. Unlike foundation issues, which are largely hidden from view, structural design flaws may not become apparent until the building is partially completed, or worse, after occupancy. These errors can stem from miscalculations, inadequate material selection, poor coordination between disciplines, or failure to account for environmental and dynamic loads. Understanding structural design. Structural design is the process of calculating, modeling, and detailing structural components so that they can safely support and transfer all imposed loads to the foundation and eventually to the ground. Key principles include: 1. Load assessment. O-date loads. Permanent weights such as walls, floors, roofs, and fixed equipment. O-live loads, variable weights like furniture, occupants, or storage. O-environmental loads, wind, snow, rain, earthquakes, and soil pressure. Proper calculation ensures that each member, from beams to columns, can carry the intended load safely. 2. Material selection. O-concrete, steel, timber, and composites each behave differently under load. Using substandard or inappropriate materials can lead to overstressed members or brittle failures. 3. Structural systems and layout. Load paths must be clearly defined so forces are efficiently transferred from slabs to beams, columns, and foundations. Poorly planned layouts can cause localized stress concentrations, resulting in cracks or excessive deflection. 4. Code compliance. Structural engineers must adhere to local building codes, international standards, and safety regulations. Non-compliance can compromise safety and lead to legal liability. Common structural design flaws. 1. Under-designed members. Beams, columns, or slabs that are too small for the applied loads can fail prematurely. This often occurs due to miscalculations or assumptions about live loads. 2. Overlooked load combinations. Engineers must consider all possible load scenarios, including simultaneous dead, live, and environmental loads. Failure to do so can result in structural overstressing during extreme events. 3. Poor integration of disciplines. Lack of coordination between architectural, mechanical, electrical, and structural designs can cause conflicts, such as penetrations through beams, reducing their load-carrying capacity. 4. Improper reinforcement detailing. Concrete members rely on steel reinforcement to resist tension. Incorrect placement, insufficient cover, or underestimation of stress can cause cracks, spalling, or collapse. 5. Ignoring foundation interaction. Structural designs must account for the type and behavior of the foundation. Ignoring soil structure interaction can result in settlement-induced stress in structural members. 6. Lack of redundancy. A well-designed structure includes multiple load paths. Lack of redundancy can cause progressive collapse if one member fails. Consequences of structural design flaws. Structural design flaws can manifest in various ways, including visible cracks in beams, columns, or slabs. Even hairline cracks indicate stress concentrations that may worsen over time. Excessive deflection or vibration. Floors or beams that bend or oscillate under normal loads signal insufficient stiffness. Partial or complete collapse. In extreme cases, design flaws combined with external factors like earthquakes or heavy snow loads can lead to catastrophic failure. Increased maintenance costs. Poor design leads to frequent repairs, retrofitting, or strengthening interventions. Professional measures to prevent structural failures. Structural engineers and construction professionals use multiple strategies to prevent design-related failures. 1. Comprehensive load analysis. Calculate all date, leaf, and environmental loads with conservative safety factors. 2. Advanced modeling and simulation. Utilize software such as ETABS, SAP 2000, STAAD.Pro, or BIM-based structural analysis to simulate load behavior and identify weak points. 3. Peer reviews and independent checks. Critical projects undergo multiple rounds of structural verification by independent engineers. 4. Material testing and verification. Confirm that all concrete, steel, and other materials meet or exceed design specifications. 5. Coordination across disciplines. Structural engineers work closely with architects, MEP engineers, and contractors to ensure all penetrations, supports, and loads are accounted for. 6. Incorporating redundancy and safety factors. Design members with additional capacity and multiple load paths to handle unexpected loads. Real-world examples. Office tower with under-designed beams. Early cracking was observed in floor beams due to underestimated live loads. Engineers reinforced the beams with additional steel and carbon fiber sheets, preventing further damage. Residential apartment with poor integration. HVAC ducts penetrated a main beam, reducing its effective area. The design team reworked reinforcement and load paths, restoring structural integrity. Industrial facility with overlooked seismic loads. A warehouse in an earthquake-prone region was initially designed without considering lateral forces. Retrofitting shear walls and bracing systems prevented catastrophic failure. Parking structure with inadequate redundancy. Partial failure of a column was avoided because the structure had multiple load paths, demonstrating the importance of redundancy. Key lessons for professionals. 1. Design integrity is critical. A flawless foundation is insufficient if the superstructure cannot handle the loads imposed on it. 2. Simulation and peer review save lives and costs. Early identification of flaws reduces construction delays, rework, and potential hazards. 3. Coordination prevents conflict. Early collaboration between all disciplines prevents design conflicts that compromise safety. 4. Redundancy and safety margins protect against uncertainty. Unpredictable environmental or human factors can never be eliminated, only mitigated through smart design. 5. Continuous monitoring during construction. Observing member behavior under partial loading allows engineers to identify and correct issues before final occupancy. Section 3. Material defects and workmanship errors. Construction is not just about design and foundations, it is equally about materials and execution. Even a perfect structural design fails if materials are substandard or workmanship is poor. Understanding material defects and workmanship errors is critical because they are among the most frequent contributors to construction failures worldwide. Understanding material defects. Materials in construction. Concrete, steel, timber, masonry, composites, and finishes must meet strict specifications for strength, durability, and performance. However, defects can occur due to 1. substandard material quality. O. Concrete with incorrect mix ratios or insufficient curing. O. Steel reinforcement with low tensile strength or corrosion. O. Bricks, blocks, or masonry units that fail compressive strength tests. 2. Manufacturing or supply issues. Materials sourced from unreliable suppliers may not comply with standards. This includes incorrectly fabricated steel, defective precast elements, or low-quality timber. 3. Storage and handling problems. Improper storage can damage materials. O. Steel exposed to moisture may rust. O. Timber left outdoors may warp or rot. O. Cement stored improperly may clump and lose binding capacity. 4. Environmental exposure. Extreme temperatures, humidity, or sunlight can degrade material properties before use. For example, concrete cured in freezing temperatures without precautions may fail strength tests. Common workmanship errors. Even high-quality materials can fail if they are improperly handled, installed, or executed. Typical workmanship errors include: 1. Concrete issues. O. Incorrect mixing ratios or over/underwatering. O. Poor compaction or inadequate curing. O. Placement without proper formwork, leading to honeycombing or voids. 2. Steel reinforcement errors. O. Incorrect bar placement or spacing. O. Insufficient concrete cover, leading to corrosion. O. Poor splicing or anchoring, reducing structural continuity. 3. Masonry and brickwork defects. O. Uneven mortar joints. O. Misaligned walls. O. Weak bonding, reducing load transfer and durability. 4. Waterproofing and finishes. O. Improper membrane application. O. Incomplete joint sealing. O. Failures leading to leaks, efflorescence, or mold growth. 5. Mechanical and electrical installation errors. O. MEP penetrations through structural elements without proper reinforcement. O. Poor pipe or conduit alignment leading to leaks or electrical hazards. Consequences of material and workmanship defects. Material defects and poor workmanship can result in structural cracks and deformation. Concrete slabs may crack, beams may deflect. Premature corrosion and material degradation. Steel reinforcement exposed to moisture corrodes. Water infiltration. Improper waterproofing leads to foundation or wall damage. Reduced load-bearing capacity. Misplaced steel or low-quality concrete reduces the safety margin. Increased maintenance costs, ongoing repairs, retrofitting, or partial reconstruction. Project delays and financial loss. Defective work often requires rework, slowing schedules and increasing budgets. Professional measures to prevent material defects and workmanship errors. 1. Strict material testing and verification. O. Concrete slump tests, compressive strength tests, and reinforcement tensile tests. O. Laboratory verification of masonry, timber, and composite materials. 2. Supplier audits and quality assurance. O. Only certified and reliable suppliers are allowed. O. Materials inspected upon delivery for defects or deviations. 3. On-site supervision and training. O. Experienced supervisors monitor placement and installation. O. Workers receive training on best practices for concrete pouring, reinforcement placement, masonry, and finishing. 4. Curing and protection practices. O. Concrete cured with proper moisture, temperature, and formwork protection. O. Materials shielded from moisture, sunlight, or physical damage. 5. Documentation and record keeping. O. Material test reports, batch records, and inspection logs ensure traceability. O. Ensures accountability and prevents repeated errors. Real-world examples. High-rise concrete slab defect. Improper compaction during placement caused honeycombing in a floor slab. Immediate inspection and partial replacement prevented structural failure. Industrial facility with steel corrosion. Steel beams were delivered exposed to rain, causing rust. Engineers replaced affected sections and implemented proper storage protocols. Residential project with masonry issues. Walls exhibited uneven settling due to weak mortar. Corrective work included repointing, strengthening, and proper curing procedures. Waterproofing failure in parking garage. Leaks developed due to incomplete membrane application. Reinstallation and thorough inspection prevented long-term structural damage. Lessons learned. 1. High-quality materials alone are not enough. Even premium concrete, steel, or timber fail without proper handling, placement, and curing. 2. Supervision saves projects. Continuous on-site monitoring detects errors early and prevents expensive rework. 3. Training reduces human error. Skilled labor ensures accurate placement of reinforcement, proper masonry work, and correct installation of waterproofing and finishes. 4. Documentation ensures accountability. Keeping material test reports, inspection logs, and photographs is critical for quality assurance and legal compliance. 5. Proactive measures minimize risk. By combining quality materials, skilled labor, supervision, and testing, professionals can eliminate most defects before they threaten structural integrity. Section 4. Waterproofing and moisture problems. Water is both essential for life and one of the greatest enemies of construction. While soil and structural design form the backbone of a building, water intrusion and moisture accumulation are silent threats that gradually compromise strength, safety, and durability. Proper waterproofing and moisture management are crucial to prevent long-term damage to foundations, slabs, walls, and finishes. Understanding water as a risk factor. Moisture affects nearly every aspect of construction. 1. Foundations. Saturated soil reduces load-bearing capacity and can cause differential settlement or heave. Poor drainage leads to hydrostatic pressure on basement walls, resulting in cracks or leaks. 2. Structural members. Reinforced concrete relies on steel to resist tension. Moisture penetration leads to corrosion, spalling, and weakening of beams and slabs. 3. Finishes and interiors. Water infiltration can cause paint blistering, efflorescence, mold growth, and deterioration of finishes, compromising aesthetics and hygiene. 4. Mechanical and electrical systems. Moisture can damage electrical wiring, HVAC systems, and plumbing, posing safety risks and requiring costly repairs. Common causes of waterproofing and moisture problems. 1. Poor foundation drainage. Water accumulation around footings or basements exerts hydrostatic pressure, leading to wall cracks and seepage. 2. Substandard waterproofing materials. Low-quality membranes, coatings, or sealants fail under stress, degrade under UV exposure, or peel away from surfaces. 3. Improper installation. Or membranes applied without proper priming. Or incomplete joint sealing. Or punctures or wrinkles in sheets. 4. Design flaws. Or lack of slope for water runoff on terraces or roofs. Or insufficient protection for exposed walls. Or no separation between structural and waterproofing layers. 5. Construction defects. Or cracks in concrete due to shrinkage or poor curing. Or misaligned expansion joints. Or improper detailing around penetrations, balconies, or roof drains. 6. Environmental and climatic factors. Or heavy rainfall, flooding, or snow accumulation. Or high groundwater levels. Or seasonal moisture variation causing expansion and contraction of materials. Consequences of moisture problems. 1. Structural damage. Or corrosion of steel reinforcement in slabs and beams. Or spalling of concrete surfaces. Or weakening of masonry walls and plaster. 2. Health and safety issues. Or mold and mildew growth leading to respiratory hazards. Or slippery surfaces and indoor dampness. 3. Aesthetic and functional degradation. Or blistered paint and efflorescence on walls. Or staining and material decay. Or reduced lifespan of finishes and fixtures. 4. Economic impact. Or costly repairs or retrofitting. Or delays in project handover. Or potential legal liabilities due to non-compliance with standards. Professional strategies to prevent waterproofing and moisture problems. 1. Comprehensive site assessment. Evaluate soil moisture, groundwater table, rainfall patterns, and drainage conditions before construction. 2. Appropriate waterproofing systems. Or basement and foundation, use robust membranes, damp-proofing coatings, and perimeter drains. Or roof and terrace, apply liquid-applied membranes, shut membranes, or combination systems with proper slope for drainage. Or wet areas. Bathrooms and kitchens require specialized coatings and sealants. 3. Proper installation techniques. Or membranes should be installed on clean, dry, and level surfaces. Or overlaps, joints, and penetrations must be carefully sealed. Or surfaces should be cured and primed according to manufacturer instructions. 4. Drainage and water management. Or perimeter drains around foundations. Or French drains or sump pumps for high water table areas. Or gutters, downspouts, and roof slopes to direct water away from structures. 5. Regular inspection and maintenance. Or check membranes, joints, and coatings during and after construction. Or early detection of leaks or cracks prevents long-term damage. Real-world examples. High-rise residential tower. A poorly waterproof podium slab led to leaks during the first monsoon. Engineers removed defective membrane sections, reapplied a reinforced liquid membrane, and added slope improvements, preventing damage to interiors and finishes. Basement parking structure. Hydrostatic pressure caused wall seepage. Installation of perimeter drains and injection of waterproofing compounds successfully mitigated water infiltration. Commercial office building roof. Flat terrace without proper slope led to ponding water. Retrofitting involved applying a high-performance sheet membrane and adjusting slope for runoff, preventing leaks and concrete deterioration. Industrial facility. Improper detailing around service penetrations caused localized water ingress. Engineers corrected penetrations using specialized sealants and reinforced membranes. Lessons learned. 1. Waterproofing must be planned from day one. Retrofitting waterproofing is expensive and less effective than initial planning and proper installation. 2. Material quality and installation are equally important. Even the best membrane fails if improperly installed or punctured during construction. 3. Environmental conditions cannot be ignored. Groundwater levels, rainfall intensity, and soil type must dictate waterproofing strategy. 4. Inspection and maintenance prevent future failures. Continuous monitoring ensures early detection of leaks or membrane degradation. 5. Holistic approach saves cost and time. Combining drainage, membrane selection, slope design, and professional installation minimizes both structural and aesthetic damage. Section 5. Safety hazards and labor issues. Construction is inherently a high-risk industry. Unlike office-based work, construction combines heavy machinery, working at heights, live electrical systems, hazardous materials, and large labor teams, all in dynamic environments. Safety hazards and labor issues are therefore critical factors that not only endanger human life but also directly affect project timelines, costs, and quality. Understanding safety hazards in construction. 1. Falls from heights. One of the most common causes of accidents, falls occur due to unprotected edges, improper scaffolding, or lack of fall arrest systems. Even a small misstep on a high-rise floor can result in serious injury or death. 2. Falling objects. Tools, debris, or construction materials dropped from scaffolds or cranes can injure workers or damage property. Proper barriers, toeboards, and signage are essential preventive measures. 3. Electrical hazards. Live wires, temporary power supplies, or contact with energized equipment can lead to shocks, burns, or fatalities. Safety protocols, grounding, and PPE, personal protective equipment, are crucial. 4. Machinery and equipment risks. Heavy machinery like cranes, excavators, or forklifts pose risks if misused or improperly maintained. Pinching, crushing, or run-over accidents are common. 5. Hazardous materials. Exposure to chemicals, dust, asbestos, or wet concrete can cause health issues, ranging from skin irritation to respiratory illnesses. 6. Structural failures during construction. Incomplete frameworks, unsupported formwork, or partially erected scaffolding can collapse, posing significant dangers. 7. Fire hazards. Welding, flammable materials, and electrical faults increase the risk of on-site fires. 8. Environmental hazards. Extreme weather, flooding, high winds, or seismic activity can exacerbate all other risks. Labor issues and their impact. 1. Inadequate training. Untrained laborers may misuse tools, ignore safety protocols, or make workmanship errors, resulting in accidents or defective work. 2. Poor supervision. Lack of oversight allows unsafe practices and mistakes to go unnoticed until they cause problems. 3. Fatigue and overwork. Extended shifts, insufficient breaks, and high physical demand reduce attention and increase the likelihood of accidents and errors. 4. Communication gaps. Miscommunication between supervisors, engineers, and laborers often leads to mistakes, unsafe practices, or inconsistent quality. 5. Labor turnover. High turnover leads to inexperienced workers on site, increasing the potential for accidents and defects. Consequences of safety hazards and labor issues. 1. Human costs. Injuries, disabilities, and fatalities are the most severe consequences. Beyond the human tragedy, they create legal and ethical liabilities. 2. Financial costs. Medical expenses, insurance claims, compensation, and legal penalties can inflate project budgets significantly. 3. Project delays. Accidents often halt work, disrupt schedules, and require reallocation of labor and resources. 4. Reduced quality. Unsafe or overworked teams may cut corners, leading to material defects or incomplete workmanship. 5. Reputation damage. Repeated accidents and poor labor management reflect negatively on contractors, engineers, and project stakeholders. Professional measures to mitigate hazards and labor issues. 1. Comprehensive safety planning. Conduct risk assessments for every activity. Identify high-risk areas and implement safety controls. 2. safety training and awareness programs. O. Educate laborers on PPE usage, hazard recognition, and emergency response. O. Regular toolbox talks and refresher courses. 3. Use of PPE, personal protective equipment. Helmets, harnesses, gloves, goggles, safety boots, and respiratory protection must be mandatory. 4. Supervision and monitoring. O. Safety officers and site managers continuously monitor compliance. O. Daily inspections ensure adherence to protocols. 5. Equipment and machinery management. O. Regular maintenance and inspections. O. Proper training for operators. O. Lockout/tagout procedures for electrical equipment. 6. Safe work design. O. Scaffolds, ladders, and formwork must meet design and load standards. O. Guardrails, toe boards, and safety nets installed in elevated areas. 7. Emergency preparedness. O. Fire extinguishers, first aid kits, and evacuation plans. O. Train personnel for emergency response. 8. Labor management practices. O. Adequate rest periods and rotation of shifts. O. Clear communication channels between supervisors and teams. O. Skill assessments and mentoring for new workers. Real-world examples. High-rise residential project. A worker fell from a partially erected scaffold due to missing guardrails. The site management immediately installed safety nets, provided harnesses, and retrained the labor force, preventing further accidents. Commercial building electrical installation. Temporary live wiring caused a minor fire. Engineers implemented lockout/tagout procedures and conducted safety workshops to eliminate similar risks. Industrial facility with heavy machinery. Improper crane operation led to material dropping. Corrective measures included operator certification, equipment inspection protocols, and strict supervision. Infrastructure project with fatigue labor. Long shifts without rotation resulted in defective concrete placement. Adjusted work schedules, break policies, and training programs improved safety and quality. Lessons learned. 1. Safety is non-negotiable. Human life and health are paramount. No deadline or budget pressure justifies compromising safety. 2. Training reduces risk. Well-trained labor reduces accidents and ensures better workmanship. 3. Proactive supervision prevents failure. Continuous oversight detects unsafe practices and prevents accidents before they escalate. 4. Emergency preparedness saves lives. Having clear procedures for accidents, fire, and equipment failure is critical. 5. Labor management affects quality. Skilled, rested, and motivated teams not only work safely but also maintain higher construction quality. Section 6. Equipment and labor inefficiencies. Construction projects rely heavily on both equipment and labor. While skilled labor provides the expertise to execute complex tasks, equipment enables efficiency, precision, and speed. Mismanagement of either can result in cost overruns, delays, and compromised quality, which are common reasons why construction projects fail. Understanding equipment inefficiencies. Equipment inefficiency occurs when machinery is underutilized, poorly maintained, or mismatched to the task. Key contributing factors include 1. Inadequate equipment planning. Or using the wrong machinery for site conditions or material types. Or underestimating equipment capacity leading to repeated cycles or slow production. 2. Poor maintenance. Or breakdown of critical machinery such as cranes, excavators, or concrete pumps delays operations. Or neglected routine inspections can lead to catastrophic failures. 3. Operator skill deficiency. Untrained operators may mishandle equipment, causing accidents, wastage, or structural damage. Poor coordination between operators and ground teams increases risk. 4. Scheduling conflicts. Multiple tasks requiring the same equipment can lead to bottlenecks. Idle time increases costs and reduces overall productivity. 5. Fuel and energy mismanagement. Inefficient fuel usage, improper storage, or energy wastage adds to operational costs. Labor inefficiencies and their impact. Even with advanced equipment, labor inefficiency can reduce productivity and quality. Common causes include 1. Lack of skill or training. Workers may take longer to complete tasks or produce substandard workmanship. Improper handling of materials and tools increases the risk of defects. 2. Poor supervision. Without oversight, laborers may deviate from standard procedures. Safety compliance and quality control suffer. 3. Fatigue and motivation issues. Long shifts, repetitive tasks, and lack of incentives reduce output quality and speed. Mistakes and accidents increase under fatigue. 4. Coordination and communication gaps. Misalignment between trades, equipment operators, and labor teams slows workflow. Delayed handovers between tasks increase idle time. 5. Resource allocation problems. Incorrect assignment of skilled workers or specialized operators can create bottlenecks. Overstaffing or understaffing disrupts workflow balance. Consequences of equipment and labor inefficiencies. 1. Project delays. Equipment breakdowns or slow labor directly impact schedules, causing delays that cascade across tasks. 2. Cost overruns. Idle labor, fuel wastage, repeated rework, and overtime contribute to budget escalations. 3. Reduced quality. Inefficient execution often results in defects, poor finishes, and the need for corrections. 4. Safety risks. Poorly managed equipment or fatigued workers increase the likelihood of accidents. 5. Lower morale and productivity. Inefficiencies frustrate teams, affecting motivation and overall project culture. Professional measures to improve efficiency. 1. Equipment planning and selection. Match machinery to site conditions and task requirements. Consider load capacity, reach, mobility, and precision. 2. Regular maintenance and inspections. Preventive maintenance schedules reduce breakdowns. Proper lubrication, cleaning, and servicing extend equipment life. 3. Operator training programs. Ensure all operators are certified and skilled. Provide ongoing refresher courses for advanced techniques. 4. Labor management and training. Assign tasks according to skill level. Provide targeted training in complex or hazardous tasks. Implement mentorship programs for new workers. 5. Efficient scheduling and coordination. Use project management software to allocate equipment and labor efficiently. Monitor workflow to prevent bottlenecks and idle time. 6. Motivation and incentives. Recognize high performance, punctuality, and quality workmanship. Encourage teamwork and accountability. 7. Monitoring and reporting. Daily progress reports, checklists, and performance metrics help identify inefficiencies early. Adjust workflows in real time to improve productivity. Real-world examples. High-rise construction project. Repetitive delays in concrete pouring were traced to an incorrectly scheduled concrete pump. Rescheduling equipment and coordinating labor resulted in faster cycle times and fewer delays. Industrial warehouse. Poorly trained crane operators cause minor accidents and material damage. Implementing a structured operator training program improves safety and speed of operations. Commercial office complex. Idle labor and uncoordinated shifts slowed flooring installation. Reorganization of labor teams and task sequencing reduced project duration and improved quality. Residential project. Multiple teams sharing one earth-moving machine caused bottlenecks. By leasing an additional machine and revising schedules, the workflow improved, eliminating delays. Lessons learned. 1. Efficiency requires planning and skill. Proper selection, maintenance, and operation of equipment combined with trained, motivated labor ensures timely, high-quality construction. 2. Coordination prevents waste. Scheduling equipment and labor in harmony avoids idle time and rework. 3. Monitoring improves productivity. Tracking equipment usage and labor performance helps identify inefficiencies early. 4. Training reduces risks and improves quality. Well-trained operators and workers handle equipment properly and follow best practices, reducing defects and accidents. 5. Proactive problem-solving saves time and money. Addressing minor inefficiencies immediately prevents major delays and cost overruns. Section 7. Design changes and client modifications. One of the most challenging aspects of construction project management is handling design changes and client-driven modifications. While flexibility is important to meet client needs, late or poorly managed changes can disrupt schedules, inflate costs, and compromise quality. Professionals must strike a delicate balance between accommodating requests and maintaining project integrity. Understanding the nature of design changes. Design changes can occur for a variety of reasons. 1. Client requirements. Or last-minute preferences in layouts, finishes, or materials. Or additional features such as elevators, terraces, or interior upgrades. 2. Regulatory or code compliance. Or adjustments required to meet updated building codes or local regulations. Or environmental or safety compliance modifications. 3. Site conditions. Or unanticipated soil or structural constraints requiring design adjustments. Or changes in foundation or structural systems to adapt to real-world conditions. 4. Coordination errors or omissions. Or conflicts between architectural, structural, and MEP designs may require rework. Or oversights detected during inspections or quality checks. 5. Technological advancements or material availability. Or substituting materials due to supply issues. Or upgrading systems or finishes to more efficient or sustainable options. Risks introduced by design changes. Even minor modifications can have significant ripple effects on construction projects. 1. Schedule delays. Or rework, redesign, and procurement of new materials at time. Or coordination with subcontractors and labor teams slows progress. 2. Increased costs. Or change orders can escalate budgets due to new materials, labor, and equipment. Or unplanned design revisions often require additional professional fees. 3. Quality compromise. Or rapidly implemented changes may not follow standard procedures. Or increased risk of defects if materials or construction methods are altered hastily. 4. Structural and safety risks. Or unreviewed modifications can affect load distribution or structural stability. Or changes in MEP systems may interfere with fire safety, ventilation, or electrical safety. 5. Communication breakdown. Or multiple stakeholders may misunderstand or misinterpret changes. or misaligned documentation can lead to errors and omissions. Professional strategies for managing design changes. 1. Early and continuous communication. Or establish clear channels between client, architect, engineer, and contractor. Or document all discussions, approvals, and decisions. 2. Change order management system. Or formal process for evaluating, approving, and tracking changes. Or includes cost impact, schedule impact, and risk assessment. 3. Impact analysis. Or engineers and project managers assess structural, schedule, and financial consequences. Or identifies whether changes are feasible without compromising safety or quality. 4. Integrated design approach. Or use BIM, building information modeling, to visualize impacts across disciplines. Or ensure changes are coordinated between architectural, structural, and MEP systems. 5. Prioritization and phasing. Or implement critical changes immediately while deferring non-critical modifications to appropriate phases. Or avoid introducing changes that disrupt ongoing construction activities unnecessarily. 6. Documentation and version control. Or maintain updated drawings, specifications, and schedules. Or track revisions to prevent miscommunication or outdated instructions. 7. Contingency planning. Or allocate buffer time and budget for potential changes. Or include flexibility in procurement and resource allocation. Real-world examples. Residential high-rise. A client requested an upgraded kitchen layout mid-construction. Engineers revised structural slab openings and MEP routing, while project managers coordinated new material procurement, preventing delays and structural issues. Commercial office tower. Regulatory changes required additional fire-rated walls. The team analyzed load paths, reconfigured partitions, and updated schedules to accommodate the modification efficiently. Industrial facility expansion. A client requested increased storage capacity, affecting floor load distribution. Engineers recalculated structural loads, added reinforcement, and coordinated with labor teams to implement safely. Hotel project. A last-minute interior design change required new finishes and MEP adjustments. By using BIM and integrated scheduling, the team avoided conflicts and minimized disruptions. Lessons learned. 1. Anticipate change. Flexibility should be built into schedules, budgets, and design processes to handle client or regulatory modifications without compromising safety or quality. 2. Formalize the change process. Documenting and approving every modification prevents misunderstandings and reduces disputes. 3. Evaluate impacts thoroughly. Every change should be analyzed for structural, financial, and schedule implications. 4. Coordinate across disciplines. Integration between architecture, structure, and MEP ensures changes do not compromise other systems. 5. Communicate clearly with clients. Explain consequences, costs, and risks associated with modifications to manage expectations effectively. 6. Leverage technology. BIM, project management software, and digital documentation tools allow teams to implement changes efficiently while maintaining quality and safety. Section 8. Scheduling and cost overruns. One of the most visible indicators of a troubled construction project is a delayed schedule or a budget that has ballooned beyond expectations. While clients often focus on final delivery dates and cost, professionals understand that schedule and cost overruns are deeply interconnected with design, materials, labor, equipment, and unforeseen risks. Mismanagement in any of these areas can ripple through the project, resulting in delays, escalating costs, and sometimes complete project failure. Understanding construction scheduling. Scheduling is the process of planning, sequencing, and allocating time for all construction activities. A robust schedule ensures that tasks are executed in logical order. Resources, labor, materials, and equipment are available when needed. Critical milestones are met without bottlenecks. Common scheduling methods include 1. Critical path method, CPM. Or identifies the sequence of tasks that determines the shortest project duration. Or delays in critical path activities directly affect project completion. 2. Gantt charts. Or visual representation of tasks, durations, and dependencies. Or useful for tracking progress and detecting potential delays. 3. Program evaluation and review technique, PERT. Or estimates task durations using optimistic, pessimistic, and most likely scenarios. Or provides probabilistic scheduling for risk-sensitive projects. 4. Resource-loaded schedules. Or aligns labor, materials, and equipment with task timelines. Or highlights potential shortages or bottlenecks before they occur. Causes of schedule delays. 1. Design changes and approvals. Or last-minute client modifications or regulatory approvals can halt ongoing work. Or redesign or rework requires additional time and resources. 2. Material delays. Or late delivery of critical materials, incorrect shipments, or poor storage practices. Or substandard materials may need replacement or testing before use. 3. Labor shortages or inefficiencies. Or absenteeism, fatigue, or untrained labor slows task completion. Or miscommunication between teams increases delays. 4. Equipment failures. Or breakdowns of cranes, pumps, or concrete mixers halt operations. Or maintenance and replacement take time, affecting schedules. 5. Unforeseen site conditions. Or soil issues, water table problems, or unexpected obstructions. Or environmental factors such as heavy rain, snow, or extreme heat. 6. Permitting and regulatory delays. Or inspections, approvals, and compliance checks can extend timelines. Or delays often affect multiple interdependent tasks. Understanding cost overruns. Cost overruns occur when actual project costs exceed the original budget, often as a consequence of scheduling delays or mismanagement. Common contributors include 1. Labor costs. Or overtime due to schedule delays. Or additional hiring to catch up on delayed tasks. 2. Material costs. Or price escalation due to delayed procurement. Or replacement of defective or damaged materials. 3. Equipment costs. Or rental charges for extended durations. Or repair or replacement of broken machinery. 4. Rework and correction costs. Or reconstructing defective work. Or revising structures due to design changes or errors. 5. Administrative and legal costs. Or contractual claims, penalties, and legal disputes. Or extra costs for project management oversight. 6. Indirect costs. Or financing, insurance, and overheads that accumulate with delays. Professional strategies to manage scheduling and cost. 1. Comprehensive planning. Or establish realistic timelines based on task complexity, resources, and environmental conditions. Or integrate buffers for unforeseen delays. 2. Detailed cost estimation. Or include labor, materials, equipment, contingency, and indirect costs. Or regularly update estimates based on market trends and procurement status. 3. Risk assessment and mitigation. Or identify high-risk tasks and plan mitigation strategies. Or allocate contingency budgets for potential design changes or site challenges. 4. Resource optimization. Or assign labor and equipment based on task priority. Or prevent idle time and ensure balanced workload distribution. 5. Progress monitoring. Or track milestones, task completion, and resource usage. Or use project management software to detect potential delays early. 6. Change management process. Or evaluate cost and schedule implications of design changes before implementation. Or ensure proper approval and documentation. 7. Collaboration and communication. Or maintain coordination between architects, engineers, contractors, and suppliers. Or clear communication reduces misunderstandings and prevents delays. 8. Regular audits and reviews. Or conduct monthly or weekly audits to evaluate schedule adherence and cost performance. Or correct deviations proactively rather than reactively. Professional strategies to manage scheduling and cost. 1. Comprehensive planning. Or establish realistic timelines based on task complexity, resources, and environmental conditions. Or integrate buffers for unforeseen delays. 2. Detailed cost estimation. Or include labor, materials, equipment, contingency, and indirect costs. Or regularly update estimates based on market trends and procurement status. 3. Risk assessment and mitigation. Or identify high-risk tasks and plan mitigation strategies. Or allocate contingency budgets for potential design changes or site challenges. 4. Resource optimization. Or assign labor and equipment based on task priority. Or prevent idle time and ensure balanced workload distribution. 5. Progress monitoring. Or track milestones, task completion, and resource usage. Or use project management software to detect potential delays early. 6. Change management process. Or evaluate cost and schedule implications of design changes before implementation. Or ensure proper approval and documentation. 7. Collaboration and communication. Or maintain coordination between architects, engineers, contractors, and suppliers. Or clear communication reduces misunderstandings and prevents delays. 8. Regular audits and reviews. Or conduct monthly or weekly audits to evaluate schedule adherence and cost performance. Or correct deviations proactively rather than reactively. Section 9. Regulatory and environmental compliance issues. Construction projects operate in a highly regulated environment. Compliance with local building codes, environmental regulations, safety standards, and permit requirements is essential. Failure to adhere to these rules can halt construction, increase costs, create legal liabilities, and even endanger lives. Regulatory and environmental compliance is therefore a critical aspect of professional construction management. Understanding regulatory compliance. Regulatory compliance refers to following legal requirements, building codes, and safety standards throughout the construction process. Key components include 1. Building codes. Or structural design, fire safety, electrical, and mechanical systems must comply with local codes. Or codes often specify load calculations, material standards, and construction techniques. 2. Zoning and permits. Or land use regulations, building heights, and floor area ratios are strictly controlled. Or permits must be obtained for excavation, structural work, and specialized installations. 3. Occupational safety and health standards. Or OSHA-like regulations require proper PPE, hazard management, and training programs. Or non-compliance can result in work stoppages, fines, or accidents. 4. Environmental regulations. Or construction may impact air, water, and soil quality. Or environmental impact assessments, pollution control measures, and waste management plans are required. 5. Contractual and legal obligations. Or compliance with contract specifications and legal requirements ensures project legitimacy and avoids disputes. Common compliance issues. 1. Permit delays or omissions. Or construction may begin without proper permits, risking fines or legal action. Or changes in regulatory requirements can invalidate existing approvals. 2. Code violations. Or structural, electrical, or fire safety deviations may compromise safety. Or improper documentation or inspections often lead to non-compliance. 3. Environmental oversights. Or poor erosion control, waste management, or pollution prevention can halt work. Or unplanned land disturbance may violate environmental protection laws. 4. Health and safety non-adherence. Or lack of PPE, unsafe scaffolding, or inadequate training violates safety standards. Or accidents can lead to government investigations and project suspension. 5. Documentation and record-keeping failures. Or missing inspection reports, material certifications, or change approvals can cause compliance issues. Consequences of non-compliance. 1. Legal penalties. Or fines, work stoppages, and lawsuits are common outcomes of violations. 2. Project delays. Or non-compliance may halt construction until corrective measures are implemented. 3. Increased costs. Or rectifying code violations, environmental damage, or missing permits adds significant expenses. 4. Reputation damage. Or contractors, engineers, and clients may face public scrutiny for non-compliance. 5. Safety and environmental risks. Or non-compliance may compromise structural safety or environmental integrity. Professional strategies for ensuring compliance. 1. Early regulatory assessment. Or identify applicable codes, permits, and environmental requirements during planning. 2. Integrated compliance management. Or combine legal, safety, and environmental checks into project management processes. Or use software to track approvals, inspections, and documentation. 3. Regular inspections and audits. Or schedule inspections at critical milestones. Or conduct internal audits to detect potential compliance gaps. 4. Environmental protection measures. Or implement erosion control, waste management, and pollution prevention. Or use green construction practices where feasible. 5. Training and awareness programs. Or ensure all labor, engineers, and managers understand compliance requirements. 6. Documentation and record keeping. Or maintain complete logs of inspections, approvals, and material certifications. 7. Proactive engagement with authorities. Or early and continuous communication with regulatory agencies reduces delays. Real-world examples. High-rise office project. Initial permit applications were incomplete. Early engagement with authorities and prompt documentation corrected the process, avoiding schedule disruption. Residential complex. Soil excavation exceeded environmental limits. Engineers implemented erosion controls, replanted disturbed areas, and documented mitigation, preventing fines. Industrial facility. Non-compliant electrical installations were detected during inspection. Immediate corrective measures, retraining, and updated plans restored compliance without major delays. Commercial mall. Safety audits revealed missing PPE and unsafe scaffolding. Corrective measures included PPE distribution, supervision reinforcement, and training workshops, ensuring adherence to safety codes. Lessons learned. 1. Compliance must be integrated, not optional. Legal, safety, and environmental requirements should be part of daily construction management. 2. Early planning prevents delays. Proactive permit acquisition and regulatory assessments avoid stoppages and fines. 3. Continuous monitoring is crucial. Regular inspections detect deviations before they escalate into legal or safety issues. 4. Documentation ensures accountability. Accurate records of approvals, inspections, and materials demonstrate compliance and support legal defense. 5. Training reduces risk. Educating all personnel about compliance standards minimizes human error and project risk. Section 10. Inspection and handover failures. Inspection and handover are critical stages in the life cycle of a construction project. Even a perfectly executed project can suffer long-term issues, cost overruns, or legal disputes if inspections are missed or handover is poorly managed. These stages ensure that the completed structure meets all design specifications, quality standards, safety regulations, and client expectations before it becomes operational. Understanding inspections in construction. Inspections are the process of systematically reviewing work at different stages of construction to ensure it complies with approved plans, building codes, quality standards, and safety requirements. They can include 1. Foundation inspections. Verifying soil compaction, rebar placement, and concrete quality. Ensuring proper waterproofing and drainage systems. 2. Structural inspections. Checking beams, slabs, columns, and load-bearing elements. Verifying that structural designs have been implemented accurately. 3. Mechanical, electrical, and plumbing (MEP) inspections. Ensuring HVAC, electrical wiring, and plumbing systems are installed correctly. Checking for potential conflicts between systems. 4. Safety inspections. Verifying compliance with safety protocols and building codes. Inspecting scaffolding, guardrails, fall protection, and emergency systems. 5. Finish and quality inspections. Assessing masonry, painting, flooring, fixtures, and aesthetic elements. Ensuring materials and workmanship meet project standards. Common causes of inspection failures. 1. Incomplete or superficial inspections. Inspectors may miss defects due to time constraints or lack of training. Critical issues can go unnoticed, leading to post-handover failures. 2. Poor documentation. Missing inspection reports, checklists, or photographs. Incomplete records can complicate claims or warranty processes. 3. Lack of coordination. Different inspection teams may work in silos, missing interdependent issues. Miscommunication between contractors and inspectors can cause errors. 4. Client pressure or schedule constraints. Handover may be rushed to meet deadlines. Critical inspections may be skipped or performed hastily. 5. Defective material or workmanship. Defects in materials or construction may not be visible initially. Poor finishing, hidden leaks, or structural compromises are often discovered only after occupancy. Handover challenges. Handover is the formal transfer of responsibility from contractor to client, and failures here can create long-term problems. 1. Incomplete deliverables. or missing as-built drawings, warranties, manuals, or maintenance instructions. 2. Defects not recorded or corrected. Or punch lists may be incomplete or ignored. Or unresolved minor issues can escalate into major failures. 3. Lack of training for operations teams. Or client's facility management may be unprepared to operate systems. Or improper use of mechanical or electrical systems can cause damage. 4. Disputes over quality or compliance. Or differences between contractual expectations and delivered work. Or legal disputes can arise due to inadequate handover documentation. Professional strategies for effective inspection and handover. 1. Develop a comprehensive inspection plan. Or identify critical checkpoints from foundation to finishing. Or include frequency, responsible personnel, and scope for each inspection. 2. Use standardized checklists and documentation. Or track all inspections with detailed reports, photos, and signatures. Or maintain records for warranties, maintenance, and legal compliance. 3. Cross-disciplinary coordination. Or ensure structural, MEP, and finishing teams collaborate during inspections. Or resolve conflicts before handover to prevent costly rework. 4. Punch list management. Or create a detailed list of minor defects and track their resolution. Or ensure client sign-off only after all critical items are addressed. 5. Client training and handover orientation. Or conduct operational training for mechanical, electrical, and safety systems. Or provide manuals, maintenance schedules, and emergency procedures. 6. Quality audits and third-party verification. Or engage independent auditors for critical inspections. Or verify compliance with design specifications, codes, and standards. 7. Post-handover support. Or offer warranty and support for defect resolution. Or maintain communication with client to address emerging issues. Real-world examples. Commercial tower handover. Initial inspections missed minor plumbing leaks. Corrective measures included comprehensive re-inspection, immediate repair, and updated documentation, preventing water damage post-handover. Industrial facility. Electrical handover included a training session for the client's maintenance team, ensuring proper operation of complex systems and reducing the risk of equipment failure. Residential project. Punch list items were partially addressed. A structured post-handover audit ensured all remaining issues were resolved, avoiding tenant complaints and warranty claims. Infrastructure project. Third-party inspection identified structural misalignment in a bridge deck. Early detection allowed timely corrective action, preventing long-term safety risks. Lessons learned. 1. Inspections must be thorough and structured. Superficial inspections allow defects to propagate and compromise safety. 2. Documentation is crucial. Accurate, complete records support quality assurance, legal compliance, and maintenance planning. 3. Client engagement reduces post-handover issues. Training and orientation ensure proper use of the facility and reduce misuse-related damage. 4. Early detection prevents costly rework. Identifying and correcting defects before handover avoids schedule disruptions and additional expenses. 5. Professional oversight maintains reputation. Thorough inspection and organized handover reflect diligence and reliability of contractors and engineers. Section 11. Real-world case studies of construction failures. Understanding construction failures requires more than theory, it requires analyzing real-world cases. Each failed project offers insights into human errors, technical misjudgments, regulatory oversights, and risk management failures. By examining these examples, professionals can identify preventive measures and adopt best practices in future projects. Case Study 1: Residential Apartment Building Collapse. Background: a mid-rise residential project experienced partial structural collapse during construction. The project was behind schedule, and cost-cutting measures were implemented to save money on materials and labor. Causes of failure: 1. Foundation deficiencies, poor soil investigation and shallow footings. 2. Material quality, substandard concrete and reinforcement steel. 3. Construction oversight, lack of continuous supervision and inspection. Consequences: significant human injuries. Project delays exceeding 6 months. Financial loss and legal implications for contractors. Lessons learned: comprehensive geotechnical investigations are critical. Material testing and certification must be enforced. Continuous on-site supervision reduces risk of structural errors. Case Study 2: Commercial Podium Slab Cracks. Background: a commercial podium slab exhibited differential cracking shortly after construction. The slab was intended to carry heavy loads from retail structures above. Causes of failure: 1. Design flaws, inadequate structural load calculations. 2. Construction deficiencies, improper concrete curing and reinforcement placement. 3. Project coordination, miscommunication between structural engineers and contractors. Consequences: additional reinforcement and partial reconstruction were required. Delays in project handover and increased labor costs. Lessons learned: coordination between design and construction teams is crucial. Adhering strictly to structural engineering guidelines prevents cracks. Quality control and inspection prevent defects from escalating. Case Study 3: Bridge deck failure during construction. Background: a bridge deck collapsed partially during the pouring stage. The project involved multiple contractors, including structural engineers and subcontractors. Causes of failure: 1. Formwork failure, incorrectly assembled temporary supports. 2. Load mismanagement, concrete poured too quickly without stage support. 3. Inspection oversight, insufficient monitoring of temporary structures. Consequences: work stoppage and safety investigations. High repair costs and legal disputes with stakeholders. Schedule overruns and insurance claims. Lessons learned: temporary structures must be designed and inspected rigorously. Control sequencing of heavy loads prevents structural collapse. Independent inspections provide an additional layer of safety. Case Study 4: High-rise fire safety non-compliance. Background: during a high-rise residential project, inadequate fire safety provisions were discovered prior to occupancy. Sprinkler systems, fire exits, and alarm systems were partially installed. Causes of failure: 1. Regulatory oversight, incomplete permitting and approvals. 2. Construction negligence, delays in installing fire safety systems. 3. Communication breakdown, contractors, engineers, and inspectors were misaligned. Consequences: delayed handover to clients. Penalties from fire safety authorities. Increased costs due to retrofitting and compliance enforcement. Lessons learned: compliance checks must occur throughout the project, not just at completion. Communication between regulatory authorities, contractors, and clients ensures safety. Early identification of compliance gaps prevents delays and penalties. Case Study 5: Industrial Facility Equipment Mismanagement. Background: An industrial plant construction face equipment failure and rework during assembly of heavy machinery. Causes of failure. 1. Inadequate planning, poor scheduling of equipment use and installation. 2. Operator errors, untrained personnel mishandled machinery. 3. Inspection lapses, lack of verification for load-bearing support and equipment alignment. Consequences. Project delays of several months. Increased insurance and labor costs. Disruption of client operations and revenue losses. Lessons learned. Proper training and scheduling of equipment prevent delays. Detailed inspection of equipment installation ensures safety and operational efficiency. Collaboration between contractors, engineers, and operators mitigates risk. Key takeaways from all case studies. 1. Root cause analysis is crucial. Understanding why a failure occurred helps prevent recurrence. 2. Coordination and communication save projects. Misalignment between design, construction, and inspection teams is a frequent cause of failure. 3. Compliance and standards cannot be ignored. Regulatory, safety, and quality standards are mandatory for safe and successful projects. 4. Early detection prevents catastrophe. Continuous monitoring, inspections, and proactive problem-solving reduce the impact of errors. 5. Professional oversight ensures safety and quality. Experienced engineers, project managers, and inspectors play a critical role in mitigating risks. 6. Learning from past failures improves future outcomes. Case studies provide invaluable lessons, highlighting strategies to prevent similar failures in new projects. Section 12. Risk Management and Preventive Strategies. Construction projects are inherently risky. From the initial design phase to final handover, projects face a multitude of risks including technical, financial, operational, environmental, and human factors. Effective risk management is therefore essential for preventing delays, cost overruns, structural failures, and safety incidents. Risk management is not about eliminating all risks, which is impossible. It is about identifying, assessing, prioritizing, and mitigating risks proactively. Professionals apply structured approaches to anticipate problems and implement preventive strategies that protect project outcomes. Understanding construction risks. 1. Technical risks. Design errors, miscalculations, or inappropriate materials. Equipment failures or construction method deficiencies. Structural issues arising from unforeseen site conditions. 2. Financial risks. Cost overruns due to inaccurate estimates or inflation. Budget shortfalls from material price fluctuations. Losses due to delays, change orders, or claims. 3. Operational risks. Labor shortages, inefficiencies, or skill gaps. Scheduling conflicts between tasks and equipment. Supply chain disruptions or material delivery delays. 4. Environmental risks. Flooding, soil erosion, extreme weather, or other natural hazards. Non-compliance with environmental regulations. Site contamination or unexpected environmental findings. 5. Human and organizational risks. Miscommunication between contractors, engineers, and clients. Inadequate training or supervision. Errors caused by fatigue, inexperience, or negligence. The risk management process. 1. Risk identification. Conduct thorough site assessments, design reviews, and stakeholder consultations. List all potential risks, from structural to regulatory to environmental. 2. Risk assessment. Evaluate each risk based on likelihood and potential impact. Prioritize risks that could cause critical delays, cost increases, or safety issues. 3. Risk mitigation planning. Develop strategies to prevent, reduce, or transfer risks. Include contingency plans, insurance, alternative materials, or redundant systems. 4. Implementation of preventive measures. Apply mitigation strategies through technical, managerial, and operational actions. Monitor their effectiveness throughout the project lifecycle. 5. Monitoring and review. Continuously track project risks. Update risk registers and adjust preventive measures as conditions change. Preventive strategies employed by professionals. 1. Thorough planning and feasibility analysis. Geotechnical investigations, site surveys, and structural simulations prevent technical failures. Feasibility studies evaluate financial, operational, and environmental risks. 2. Integrated project management. Use of BIM, scheduling software, and resource allocation tools ensures coordinated execution. Transparent communication between all stakeholders reduces human errors. 3. Quality assurance and control. Systematic testing of materials and workmanship ensures compliance with standards. Early detection of defects prevents costlier rework. 4. Training and capacity building. Skilled and well-trained laborers minimize operational errors. Safety and technical training reduce accident risks. 5. Contingency and budget planning. Allocate buffers for time, cost, and resource fluctuations. Prepare backup plans for equipment, materials, and labor. 6. Insurance and legal risk management. Coverage for structural failure, accidents, or environmental damage. Clear contracts defining responsibilities and liabilities. 7. Proactive communication and coordination. Weekly or daily coordination meetings keep all teams aligned. Transparent reporting of risks and progress avoids surprises. Real-world examples of risk management. High-rise tower project. Geotechnical risk was identified early. A rough foundation was designed, preventing settlement issues and structural failure. Continuous monitoring ensured stability during construction. Industrial plant construction. Scheduling conflicts and equipment sharing were anticipated. A detailed resource plan and phased task allocation reduced delays and improved efficiency. Residential complex. Risk of material shortages was mitigated by establishing multiple suppliers and early procurement strategies. Cost overruns were avoided despite market fluctuations. Bridge construction. Environmental and weather-related risks were mitigated by planning construction schedules around dry seasons and using erosion control measures. Regular inspections prevented compliance issues and safety incidents. Lessons learned. 1. Risk management is proactive, not reactive. Waiting for problems to occur is costly. Anticipating risks early saves time and money. 2. Integrated approaches yield better results. Coordinating design, construction, inspection, and operations ensures risks are managed holistically. 3. Documentation is essential. Detailed risk registers, mitigation plans, and monitoring reports provide accountability and guidance. 4. Flexibility is key. Contingency planning allows teams to respond effectively to unforeseen challenges. 5. Professional expertise matters. Engineers, project managers, and quality inspectors play a vital role in identifying and mitigating risks. Section 13. final lessons and best practices for construction success. As we approach the conclusion of this extensive exploration into construction failures and prevention strategies, it is essential to synthesize the lessons learned across all project stages. From soil investigation and foundation design to inspections, regulatory compliance, and risk management, every step has a direct impact on the success, safety, and efficiency of construction projects. In this final section, we will discuss best practices, professional strategies, and holistic approaches that ensure long-term project success. These principles are designed for engineers, project managers, contractors, and even clients who want to mitigate risk, maintain quality, and achieve timely project delivery. 1. Comprehensive planning from day one. Success begins before the first shovel touches the ground. Proper planning addresses every aspect of the project. Site analysis, geotechnical surveys, topographical studies, and environmental assessments. Design integration, ensuring architectural, structural, and MEP systems work in harmony. Feasibility studies, evaluating technical, financial, and operational viability. Contingency planning, allocating buffers for time, cost, and unexpected challenges. Planning is the foundation of failure prevention. Projects without structured planning are prone to delays, cost overruns, and quality issues. 2. Coordination and communication across all teams. Construction projects are complex, multidisciplinary endeavors. Coordination and communication are critical. Integrated meetings, regular updates with architects, engineers, contractors, and clients. Transparent reporting, documenting progress, risks, and changes. Technology use, BIM and project management software enhance collaboration and reduce errors. Key insight, miscommunication is a leading cause of defects and delays. Professionals must ensure all teams are aligned at every stage. 3. Rigorous quality assurance and control. Every component of construction must meet engineering, safety, and aesthetic standards. Material testing, ensure concrete, steel, and other materials meet specifications. Workmanship oversight, inspect critical construction tasks, including reinforcement, curing, and finishes. Continuous monitoring, implement checkpoints from foundation to finishing. Key insight, quality control is not a one-time activity. It is an ongoing process that prevents cumulative errors. 4. Safety and compliance as non-negotiable standards. No project can be considered successful if safety and regulatory compliance are compromised. Safety protocols, PPE, fall protection, scaffolding safety, and hazard mitigation. Regulatory adherence, building codes, permits, and environmental standards. Inspection culture, regular audits, independent verification, and documentation. Key insight. Safety and compliance are directly linked to project reliability, reputation, and legal protection. 5. Risk management and preventive strategies. Risk is inherent in construction, but proactive management transforms risk into manageable challenges. Risk identification, early recognition of technical, financial, operational, and environmental risks. Mitigation planning, implement strategies to reduce probability or impact. Monitoring, track risks continuously and adjust measures as necessary. Key insight, projects that fail to plan for risk often face cascading failures, escalating costs, and missed deadlines. 6. Handling change effectively. Change is inevitable, whether due to client requests, unforeseen site conditions, or regulatory updates. Professionals must Implement change management systems, evaluate cost, schedule, and safety impacts. Communicate changes clearly, ensure all stakeholders understand revisions. Integrate changes into project plans, update schedules, resource allocation, and documentation. Key insight. Control flexibility allows projects to adapt without compromising quality or safety. 7. Lessons from case studies. Real-world failures reinforce these principles. Foundation failures. Poor SAW investigation leads to structural collapse. Prevention requires geotechnical diligence. Material and workmanship deficiencies. Substandard concrete or improper curing leads to cracks. Strict QA/QC prevents defects. Schedule and cost overruns. Unplanned delays increase budgets. Risk management and real estate planning mitigate overruns. Regulatory non-compliance. Lack of permits or environmental oversight halts projects. Proactive compliance avoids penalties. Inspection failures. Missed defects at handover cause future issues. Structured inspection and handover procedures prevent problems. Key insight. Learning from failures is as important as following best practices proactively. 8. Technology as a force multiplier. Modern construction relies on advanced tools to improve accuracy, coordination, and efficiency. BIM, building information modeling, detect conflicts, visualize designs, and streamline communication. Project management software, track schedules, costs, and resources in real time. Structural simulation tools, verify load-bearing capacity, identify potential weaknesses, and optimize designs. Digital inspection and documentation, ensure accountability and traceability at every stage. Key insight. Technology, when combined with human expertise, significantly reduces the risk of failure. 9. Continuous learning and professional development. The construction industry evolves constantly. Stay updated on codes and standards, regulations change frequently, professionals must remain informed. Adopt new techniques and materials, sustainable construction, innovative reinforcement methods, and modern equipment improve project outcomes. Learn from past projects, conduct post-project reviews to identify successes and failures. Key insight. A culture of continuous learning ensures that projects become progressively safer, more efficient, and higher quality. 10. Building a culture of accountability. Successful construction projects require a culture where every team member takes responsibility. Engineers ensure design integrity. Contractors ensure proper execution. Project managers oversee schedule, budget, and coordination. Inspectors and quality auditors verify compliance and workmanship. Key insight. Accountability reduces mistakes, improves safety, and fosters trust between all stakeholders. 11. Summary of best practices for construction success. 1. Start with thorough planning and feasibility studies. 2. Ensure integrated communication and collaboration. 3. Maintain rigorous quality assurance and control. 4. Prioritize safety and regulatory compliance. 5. Implement risk management and contingency planning. 6. Manage change systematically. 7. Leverage technology for accuracy and efficiency. 8. Learn continuously from experience and case studies. 9. Foster accountability across all teams. By adhering to these best practices, construction professionals can dramatically reduce the likelihood of failure, minimize financial loss, and ensure safe, high-quality structures. Closing thoughts. Construction is more than erecting buildings, it is about orchestrating complex processes, mitigating risks, coordinating human and technical resources, and delivering functional, safe, and sustainable structures. Failure is not inevitable, it is preventable when professionals combine knowledge, experience, technology, and proactive management. By understanding why projects fail and implementing the strategies discussed in this video, stakeholders at every level can ensure successful outcomes that are safe, efficient, and durable. Final thoughts. As we conclude this comprehensive exploration into why construction projects fail, and how professionals prevent disaster, it is important to reflect on the key lessons, the role of professional diligence, and the strategies that ensure project success. Construction is a discipline where attention to detail, proactive planning, and collaboration are not optional, they are the very foundation of every successful project. Projects do not fail suddenly. Failure often accumulates gradually through small oversights, poor planning, and mismanagement. The knowledge we have covered in this video equips stakeholders with the tools to anticipate risks, prevent errors, and execute projects with precision. Key takeaways for professionals. 1. Planning is paramount. A project's success begins before construction starts. Thorough site analysis, geotechnical investigations, and design coordination set the stage for error-free execution. 2. Quality cannot be compromised. From materials to workmanship, every detail matters. Continuous quality checks, inspections, and testing prevent long-term defects. 3. Communication and coordination save projects. Teams that communicate effectively avoid misalignment, mistakes, and costly delays. Coordination between architects, engineers, contractors, and clients ensures smooth workflow. 4. Safety and compliance are non-negotiable. Safety protocols, regulatory adherence, and environmental compliance protect lives, reduce legal exposure, and maintain trust. 5. Risk management is essential. Identifying, assessing, and mitigating risks proactively prevents cascading failures and maintains budgets and schedules. 6. Learning from failures enhances future success. Real-world examples, case studies, and post-project reviews provide invaluable lessons for future projects. 7. Technology is a force multiplier. BIM, project management software, structural simulations, and digital inspection tools increase accuracy, coordination, and efficiency. The role of professionals in preventing disaster. Construction professionals, including engineers, project managers, architects, contractors, and inspectors, are the guardians of project integrity. Their vigilance ensures foundations are secure and stable. Structures are designed and built to last. Materials meet stringent quality standards. Safety hazards are mitigated before they become accidents. Budgets and schedules remain realistic and achievable. Regulatory and environmental compliance is maintained. By acting proactively rather than reactively, professionals prevent small issues from escalating into full-scale project disasters. Final words to viewers. Every project is a lesson in discipline, foresight, and professional responsibility. While construction is inherently complex and full of risks, failure is never inevitable. With proper planning, quality management, risk mitigation, and adherence to best practices, every structure can be safe, durable, efficient, and successful. We hope this video has provided you with actionable insights, real-world examples, and professional strategies that you can apply in your projects, whether you are a student, engineer, architect, contractor, or client. By understanding why projects fail and how professionals prevent disaster, you now have the knowledge to build better, safer, and more reliable structures. Call to action. If you found this content valuable, Like and subscribe for more in-depth professional construction tutorials and masterclasses. Share this video with peers, colleagues, or anyone in the construction industry. Comment your questions or experiences with project challenges, delays, or failures. Check our playlists for additional content on construction risk management, inspection techniques, and structural engineering. Closing statement. Remember, construction is not just about building structures, it is about building trust, ensuring safety, and delivering quality that lasts for generations. By learning from failures, implementing best practices, and working with diligence and integrity, professionals can prevent disasters and elevate the standards of the construction industry worldwide. Thank you for watching, and may your future projects always stand strong, on time, and within budget.